Imagine standing in Yellowstone National Park, the ground beneath your feet trembling ever so slightly, a geyser erupting in the distance with a hiss and a roar. The air smells faintly of sulfur, and the vibrant colors of hot springs dazzle your eyes. Now, picture this. Beneath that very ground lies a colossal, fiery secret, a network of magma chambers so vast and powerful it could redefine how you see this iconic landscape. What if I told you the Earth here isn't just rock and soil, but a living, pulsing system fueled by molten rock deep below? Let's dive into the heart of Yellowstone, far beyond the surface, to uncover the true scale of its subterranean magma chambers and the hidden forces that make this place a geological marvel. Yellowstone isn't just a park, it's a supervolcano, one of the most dynamic and closely studied geological systems on Earth. Its geysers, hot springs, and bubbling mud pots are all surface clues to something much bigger, a sprawling network of magma chambers that powers this natural wonder. For decades, scientists have been piecing together what lies beneath, and in recent years, breakthroughs in technology have given us a clearer picture than ever before. This isn't just about rocks and heat, it's about understanding the heartbeat of a landscape that's been shaping our planet for millions of years. So grab a metaphorical flashlight, because we're about to go deep. To understand what's beneath Yellowstone, we need to start with the basics. Yellowstone sits atop a supervolcano, a term that sounds like it belongs in a sci-fi movie, but is very real. Unlike a typical volcano with a single conical peak, a supervolcano is defined by its ability to produce eruptions of unimaginable scale. Think 1,000 cubic kilometers of material or more. Yellowstone's last major eruption, about 640,000 years ago, formed the massive caldera that now defines much of the park's geography. This caldera, roughly 30 by 45 miles, is a scar from that cataclysmic event, a reminder of the power lurking below. At the core of this supervolcano are its magma chambers, vast reservoirs of molten rock that fuel Yellowstone's geothermal features. These aren't just single pools of lava like you might imagine under a classic volcano. Instead, they're a complex, multi-layered system with magma stored at different depths and in varying states, some liquid, some partially solid, and some a mushy mix of both. The chambers are fed by a hotspot, a plume of hot material rising from deep within the Earth's mantle, possibly as far down as 1,800 miles. This hotspot is like the engine of Yellowstone, delivering the heat and material that keep the system alive. So how do we know what's down there? We can't exactly drill into a supervolcano without risking a catastrophe, so scientists rely on cutting-edge techniques to see the subsurface. Think of it like giving the Earth an MRI. Seismic tomography is one of the key tools, using the speed and behavior of earthquake waves to map out structures beneath the surface. When seismic waves travel through different materials, say solid rock versus molten magma, they slow down or speed up, giving clues about what's down there. Recent studies, particularly those from the last decade, have revolutionized our understanding. In 2015, researchers from the University of Utah and others used seismic data to create a detailed 3D map of Yellowstone's magma chambers. They found not one, but two main reservoirs. The upper chamber, located about 3 to 9 miles below the surface, is relatively small, about 2,500 cubic miles, but still massive compared to most volcanic systems. This chamber is only about 5 to 15% molten, a slushy mix of crystal and liquid magma that fuels the park's geysers and hot springs. Below that lies a second, much larger chamber, stretching from about 12 to 28 miles deep. This lower chamber is a behemoth, estimated to hold around 10,000 cubic miles of material, with roughly 2% of it molten. To put that in perspective, it's enough magma to fill the Grand Canyon several times over. These discoveries shattered earlier assumptions that Yellowstone's magma was stored in a single shallow reservoir. Instead, we now know it's a complex, tiered system with the lower chamber feeding the upper one, which in turn powers the surface activity. The Yellowstone hotspot is the key to this whole system. Unlike most volcanoes, which form at tectonic plate boundaries, Yellowstone's supervolcano is driven by a hotspot, a column of hot, buoyant rock rising from the mantle. This hotspot has been active for at least 17 million years, leaving a trail of volcanic scars across the Snake River Plain as the North American tectonic plate drifted over it. Today, the hotspot sits directly beneath Yellowstone, supplying the heat and magma that keep the chambers active. The hotspot's influence extends far beyond the magma chambers. It heats groundwater, creating the hydrothermal systems that produce Yellowstone's famous geysers like Old Faithful. The interaction between magma, water, and rock is what makes Yellowstone so dynamic. When groundwater seeps into fractures and gets heated by the magma below, it can turn to steam and erupt, creating the spectacular displays we see on the surface. But it's the magma chambers that provide the raw energy, and their size and behavior dictate the park's long-term geological fate. Let's zoom in on these magma chambers. They're not just giant pools of glowing lava like you might see in a Hollywood movie. Instead, they're complex systems of molten rock, crystals, and gases. The upper chamber, being closer to the surface, is more dynamic. Its partially molten state, about 5 to 15% liquid magma, means it's a mix of solid crystals and liquid melt, with pockets of gas that can add pressure. This chamber is directly responsible for feeding Yellowstone's hydrothermal systems, as heat from the magma warms groundwater and drives surface activity. The lower chamber is deeper and hotter but less molten. Only about 2% of its volume is liquid. This might sound underwhelming, but 2% of 10,000 cubic miles is still an enormous amount of molten material. This chamber acts as a reservoir, slowly feeding magma to the upper chamber over long timescales. The interplay between these two chambers is critical. If the upper chamber gets too much magma or gas, it could lead to increased pressure, potentially triggering volcanic activity. Though, as we'll see, a full-scale eruption is unlikely in the near future. Our knowledge of Yellowstone's magma chambers has come a long way. Early studies in the 20th century relied on surface observations and basic geophysical data, leading to oversimplified models of a single, shallow magma chamber. But as technology advanced, so did our picture of the subsurface. In the 2000s, scientists began using GPS and satellite data to track ground deformation, which can indicate magma movement below. When the ground swells or sinks, a process called deformation, it's a sign that magma or fluids are shifting. By combining seismic tomography, GPS data, and computer modeling, researchers have built increasingly detailed maps. A 2020 study, for example, used advanced seismic techniques to reveal smaller, previously undetected magma pockets connected to the main chambers. These findings suggest the system is even more complex than we thought, with a network of magma-filled fractures and sills, horizontal magma layers, weaving through the crust. Now, let's address the elephant in the room. Is Yellowstone about to blow? The short answer is no, at least not anytime soon. Yellowstone's supervolcano has erupted 3 times in the last 2.1 million years, with the most recent at 640,000 years ago. These eruptions were massive, but they're rare. Current monitoring by the Yellowstone Volcano Observatory shows no signs of an imminent eruption. The magma chambers are stable, with no significant buildup of pressure or rapid magma influx. That said, Yellowstone is far from dormant. Smaller events like earthquakes and hydrothermal explosions happen regularly. In 2018, a geyser eruption at Steamboat Geyser marked a period of heightened activity, and the park experiences thousands of small earthquakes each year, most too tiny to feel. These are normal for a geologically active area and don't necessarily signal a coming eruption. Scientists keep a close eye on deformation, gas emissions, and seismic activity to monitor for changes, and so far, everything points to business as usual. Understanding Yellowstone's magma chambers isn't just about predicting eruptions. It's about unlocking the secrets of how our planet works. The supervolcano is a natural laboratory for studying Earth's deep processes, from mantle plumes to crustal dynamics. Its magma chambers offer clues about how volcanoes evolve, how heat moves through the Earth, and how geothermal systems function. This knowledge has practical applications too, like improving geothermal energy technologies or refining our ability to monitor other volcanic systems worldwide. For those of us who aren't scientists, Yellowstone's subsurface is a reminder of the planet's raw power. It's humbling to stand on ground that's literally simmering with molten rock, to know that the beauty of a geyser or hot spring is just a tiny expression of a much larger system. It's a call to stay curious, to keep exploring, and to respect the forces that have shaped our world for billions of years. So, what's truly beneath Yellowstone? It's not just magma chambers or a hotspot. It's a story of Earth's restless energy, written in molten rock and seismic waves. The park's geysers and hot springs are just the surface chapter of a much deeper tale, one we're only beginning to understand. Thanks to modern science, we can now map these hidden chambers with unprecedented detail, revealing a system that's both awe-inspiring and humbling in its scale. Next time you see a geyser erupt or feel the warmth of a hot spring, remember, you're standing on the edge of a geological giant, one that's been alive for millions of years and will continue to shape the landscape long after we're gone. Yellowstone's magma chambers are its heartbeat, and with every new study, we get closer to hearing it loud and clear.